Hello, everyone. Welcome back to our third lesson in our Algebra 2 course. In this lesson, we'll be discussing solving linear equations. We'll look at solving them over the domain of the real numbers, and then look at how that changes as we solve equations over different domain subsets of the real numbers. All right, let's just start with this example, 3.1a. So what we're going to do is use what we learned in the previous lesson, that every number has an additive inverse, which gives you the identity. And let me show you how that works out. So we have a minus 5. And if I add 5 to minus 5, I get 0. And then, even though I don't know what x is, 2x plus 0 must be 2x, because 0 added to anything is itself. And so that's kind of the name of the game with algebra, is making zeros and ones. So we get 2x is equal to 22. And then the inverse of 2 times is 1/2. The multiplicative inverse of 2 is 1/2. So I'm going to multiply both sides by 1/2, or in other words, divide by 2. And 2 divided by 2 is 1. And I still don't know what x is, but I know that x times 1 is x, no matter what x is. So I get x is equal to 11. Now, it's very important that we check our work. As long as we didn't make a mistake, it should be correct in this lesson. But we're going to see in future lessons that even when you don't make a mistake, you still need to check your answers, because sometimes they're what we call extraneous, and they're answers that are not solutions, even though you didn't do anything wrong. So let's check. I'm going to use green pin of checking here. So to check that 11 is the solution, I simply replace x with the value of 11. And then I'm going to evaluate both sides of the expression and the equation and see if they're the same. This becomes 22 minus 5. 22 minus 5 is 17, so it worked out. Now I'm going to put my answer in solution set. So a solution set are these curly braces, and they are indicating that the set of real numbers that are solutions to this equation is the set 11. And it's a solution because when you plug it in for x and evaluate, you get a true statement. That's what a solution is. It makes an equation into a true statement. All right, let's start with a fresh page on the next on example B, though. There we go. That's better. Okay, so on this one, we are going to have to use a distributive property first to kind of simplify. So I will multiply the 2 to the 5 and the negative x, giving me 10 minus 2x, and then I'll just bring everything else straight down. Now I have some like terms. The 10 and the 7 can add to 17, and I still have a minus 2x is equal to 13. And now I'm going to subtract 17 from both sides, which gives me a negative 2x is equal to a negative 4. I'll now divide both sides by negative 2, and I get x is equal to 2. Let's check our work. So we're hoping that if I replace x with 2, that this becomes a true statement called a tautology, a provably true statement. All right, that makes 6 plus 7. Well, that is indeed 13, so it worked. You know, sometimes you'll see me put little question marks over the equal sign. I'm just saying that, is this equal? We're asking. That's just another way to document that you're checking. Well, we've got the right answer. Let's put our answer in solution set. Notice I do that after checking. All right. What's the next example for us? Okay, finally we got some x's on both sides. That's always a little bit more exciting, right? So First, I need to distribute. And when we distribute with a minus here, we need to make sure that we realize that we were minusing 3 times this whole thing. So to keep this accurate, we're going to make sure that this minus comes with this 3 when I multiply. So this becomes 5x minus 3x, and then minus 3 times 1 is 3. So the minus comes with both of them. Then I have 6x minus 5. All right, 5x minus 3x is 2x. All right, I'm going to subtract 2x from each side. I could subtract 2x's from each side, or I could subtract 6x's from each side. You'll get the same answer no matter what. Then we get negative 3 is equal to 4x minus 5. And I'll add 5 to each side. And you'll see I'm being real careful right here to make sure that I show each of these what I'm subtracting from each side, what I'm adding on both sides. And you may not need to write that down, and I'll probably stop showing that every time here in a little while, but I'm going to try and keep showing it while we're reviewing. Now I'm going to divide both sides by 4. And I can reduce this because I can divide 2/4. I can divide the top by 2 and get 1, and the bottom by 2 and get 2. So that's 1/2. All right, now we need to check. And yeah, it's a little obnoxious to have to check with a 1/2. I understand. I totally get that. But you need to understand that in general, fractions are easier to check than decimals. I know 1/2 is just 0.5, and many of you are going to want to do that. But I urge you not to. Because in general, fractions are much easier. For example, if you want to add 1/7 and 2/7, you have to add 2 7-digit numbers right there. And that's just a 7th. They get much worse. So if you're not good at doing add, subtract, multiply, divide with fractions, now's the time to keep practicing. Don't give up, because it's just going to get worse, especially when those fractions start having variables in them. Okay, since this check could be somewhat extensive, let me move this over just a little bit, and I'll use, well, let me move it over to the other side, actually. There we go. And then that's going to give me this full room over here to kind of check here. There we go. All right, so let's see what we need to do. We've got 5 times x, which is 1/2, minus 3 times 1/2 plus 1 equals 6 times 1/2 minus 5. All right, I'm going to start on the right-hand side. That one's not too bad because 6 divided by 2, remember when you multiply a whole number to a fraction, always divide first if you can. 6 divided by 2 is 3. 3 times 1 is 3. So this is 3 minus 5. So we know that the right-hand side evaluates to 2. We're just hoping that's what we get over here on the left. All right, so I can't divide 5 by 2, so I'll multiply 5. This is 5 over 1. 5 times 1 is 5. And 5 over 2. Now, I'm going to combine these two here in the middle, right? We're going to add 1/2 and 1. 1 is 1 over 1. 1 over 1. If I multiply the top and bottom by 2, I get 2 over 2. So there's my common denominator. So this is a minus 3 times 1/2 plus 2/2. Remember, 1 whole is 2 seconds. So that becomes 3/2. Keep the denominator the same. All right, now we'll multiply 3 and 3/2. And I get negative 9/2. Remember, this is 3 over 1. 3, when you multiply, it's top times top, bottom times bottom. So 9 over 2. And then 5 minus 9 is a negative 4 over 2, which is negative 2. Oh, I forgot my negative over here. 3 minus 5 is negative 2. Well, that's okay. The important thing is they check out, right? Can't believe I didn't subtract that correctly earlier. All right, so there we have it. So that is the correct answer. Let's put our answer in solution set. Very important that we do that. 1/2. Okie dokie. I think we got some more to do. Yeah, it looks like I got a couple more examples before I get to let you have a crack at it. Oh, trying to erase all that. There we go. Okay, here we are with example D coming up. All right, so I've got some fractions here to play with. The thing about fractions in an equation is I only have to keep it in fraction form if I want to, and sometimes I do, but a lot of times we would rather just get rid of the fractions, and it's really a one-step easy thing to do. So let me go over how to do that. So what you do is we're going to multiply both sides, and so since there's more than one thing on each side, we're going to have to use distributive property. But what we're going to multiply by is what's called the least common multiple. The least common multiple is simply the smallest number that can be divided evenly by both 5 and 3. So start with 5, can't divide 5 by 3, go up to 10, can't divide 10 by 3, 15. There you go. 15 is divisible by both 5 and 3. So I multiply both sides by 15. And remember my rule, when you multiply a whole number in terms of fraction, always divide first, then multiply. And if you do that, this is a piece of cake. So here we go. 15 times x over 5. Divide first. 15 divided by 5 is 3. Now multiply that times the top. 3 times x is 3x. All right, next. 15 divided by 3 is 5. And 5 times 2 is 10. All right, next, on the other side, 15 times 2 is 30. 15 times x over 3, we divide first. 15 divided by 3 is 5, and 5 times x is 5x. And because we chose a number like 15 that's divisible by 5 and 3, we're guaranteed that we're not going to have any fractions left over after that first step. So you can see it makes life really easy. All right, I am going to, I think, add 5x to both sides. And of course, there's lots of different things we could do at that moment. We could also add 10 or something like that. But I like to kind of get the x's on one side first, just a personal habit. I'll add 10 to both sides. And I get 8x is equal to 40. I'll divide both sides now by 8. And I get x equals 5. All right. Now, because we have fractions in the original problem, it's possible that this is quite a bear to check, but I don't think it's going to be too bad because I think we're not going to have too many fractions here. Well, let's just double check. All right, so if I put 5 over 5, well, that's not too bad. Minus 2/3 is equal to 2 minus 5/3. Okay, so 5 over 5 is 1. But I'm going to be kind of clever here. Let's think here. We need this to be 1, but 1 minus 2/3. So that's really 3/3. Okay? And then this is 2 over 1. So I'm going to multiply by top and bottom by 3, making it 6 over 3. And now we got everything in terms of over 3 right off the get-go. That's 1/3. 6 minus 5 is 1/3. Boom. We have a solution set of 5. All right, I get one more problem to do with you before we get to make sure that you're on board with me. Leave it over here so I can check. All right. First, I'll distribute 3 times x and 3 times 1. 2x and x makes 3x. And I've got the same amount of x's on each side. That's going to mean that it's going to be one of those special situations. So I have -3 is equal to -5. So when you lose your x's, like so when this happens here that they cancel out on both sides like this, when you lose your x's on both sides, that means that the answer is you're going to be answering the question as either no solution or all real numbers. So in this case here, no solution. because -3 never equals -5. So what that's saying is there is absolutely no value of x that you can put in that would ever make this side equal to this side. And so there's lots of different ways we could say no solution. If you want to be kind of fancy, you can draw the set for your solution set and leave it empty. It's called the empty set. I like that. You can also just simply say no solution. I'm fine with that as well. Or you'll hear us say the words no real solutions. And the reason why that makes sense is because we're dealing with the domain of real numbers. So you're saying, hey, maybe there's a solution outside of the domain of real numbers. For this particular equation, there isn't. It's really no solution in any domain that we'll ever work with. But you can say that. And then you could say this. You might see this from time to time. That is just a special symbol for this empty set. That just means the empty set. All right. So now it is time for you to do a practice problem. So what I would like for you to do, please, is work practice 3.1. Go ahead and work all the problems, not just part A. We have A, B, C, D, and that's it. So we will check back as soon as you're unpausing the video, and we'll go over them. So at this time, please pause the video. Take a second to do your best. Take your time, answer the questions, and then we'll check our work together. Okay. Well, if you're back, I hope that didn't. I hope that wasn't too tough, right? I hope you had some success, and let's go over it and see how you did. All right. So I've got 41 equals 8 minus 3x. You should just subtract 8 from each side. All right, got 41 minus 8 is 33. And, you know, some people have trouble subtracting things like that easily in their head. You know, this is not some sort of mental math contest. Feel free to, you know, do some scratch work. You know, write it nice and big on the side. I prefer it if it was on a separate sheet of paper than like some assignment paper, but you know, you can see here that 8 doesn't go on. We need to borrow, so that becomes a 3, and that becomes an 11, and then you bring down. And so there's really no problem with that. And sometimes you're just going to have to do that, especially if the subtraction gets even bigger than that. So there's definitely no harm doing that. Okay, I'm going to divide both sides by a -3, and that's going to be a negative number. Any repeated number divided by itself is 11. So that's 33 divided by 3 is 11. What I mean there is anytime you have a 2-digit number that repeats, like 99 divided by 9 is 11, 88 divided by 8 is 11. You know, but again, you know, feel free to do the long division if that's something that makes you feel more comfortable. All right, let's check. And checking is going to be really important, especially when I tell you to do it. That is part of the process. And I think you'll notice that sometimes the check is actually harder than the actual problem. And sometimes I'll have on quizzes or tests, a student will solve the algebra problem correctly, and then they'll check it and they'll mess up in their arithmetic. And then they think they got the wrong answer. And that's sad, but but that's the truth of the matter, is that it's very important that you're able to do this arithmetic, especially going on into later lessons and units in this course and in later math classes. Okay, so we have 41 is equal to 8. I have a -3 times a -11. So two negatives make it a positive, and that's going to show itself by becoming a plus 33. And then 8 plus 33 is 41. So it works. Let's put it in set notation. And we'll go on from there. All right. Next one. Okay. This one's kind of funny. It's, it just feels awkward, I think, whenever there's just an X on one side. I don't know. I always feel like it's so like an unbalanced balance beam or something. But we can handle it. So the -2 becomes a -2x, and then -2 times -1 is a +2. Excuse me. All right. I'm going to go ahead and combine the 19 and the 2 to 21. And then I'll add 2x to both sides, giving me 3x equals 21. So x is equal to 7 when we divide both sides by 3. Let's check. So the left-hand side clearly evaluates to 7. We're just hoping that the other side does as well. So that's 19 minus 2 times 6. That's 19 minus 12. And that is 7. So it checks out. All right, next up. Okay, we have some distributing to do here, don't we? I'm going to put that there and there. So this becomes 3x minus 1 equals x plus 2x. And 2 divided by 2 is 1. 1 times 1 is 1, so this is just minus 1. All right, now if 3x minus 1 is equal to x plus 2x is 3x. Okay, and then I have, wow, I have the same thing on each side. And so we could stop here, but if we subtract 3x from both sides, you will see that we end up with negative 1 equals negative 1. That's the other situation that happens when you lose all your x's. This is going to be all real numbers. And this is actually a set, right? We studied that in a previous lesson. So that actually is set notation. That is the set, the real numbers. So don't put, this is just kind of a pet peeve of mine. Don't put that because that's technically not right. That's a set of a set, which is not this class. Cool class, though. It's called topology, but we're not doing that today. So when you put real numbers, you just say all real numbers. You just put the R, or you can write out all real numbers. But that's the domain we're working with. And so we're saying that the entire domain is a solution. If we had a different domain, we would put a different number there. Or, excuse me, a different set symbol. So, checking is not necessary in this situation, okay? But I'm going to make a note here that we're going to do this just for fun, okay? Just for kicks. Just for kicks. So we're saying all real numbers are a solution. So that means that the number 7 should be a solution. Agreed? Because the 7 is a real number, right? So I'm going to put in 7. I'm always partial to 7. I don't know why. I like the number. Actually, I do know why, but I don't want to go into that today. It's a super cool number. All right, 7 minus 1/2. Okay, 3 times 7 is 21. 21 minus 1 is 20. So this is 7 plus 2 times 7 minus 1/2. Well, this is 14. I'm going to just change that. Haha. Made my 7 into a 4. So that's just 14 over 2 minus 1 over 2. That's 13 over 2. But when you multiply it times the 2 there, the 13 will just be left because 2 divided by 2 is 1. And so then you get 20 is equal to 20, which checks. And it's going to check for every other number I plug in. Pretty cool, huh? All right, but no, normally when it's no solution or all real numbers, even if I say check your solutions, you don't need to check your solutions there. But anything else, you just want to do it for fun like I did. Okay, well, this one certainly looked nasty, didn't it? I bet it made your blood pressure go through the roof and you got all panicky. But then you remembered that I said you do not have to play with the fractions. You can get rid of them on the first step, right? We just need to think of a number that is divisible by both 2 and 3, preferably the smallest number that can be divided by 3 and 2, which we call the least common multiple. So that number is 6. So I'm going to multiply both sides by 6, and as long as we've made no mistakes here, we shouldn't have... Okay, my pen is off now. There we go. Anyway, as I was saying, as long as we haven't made any mistakes, we should have no fractions when we're done with this step. So I'm going to distribute the 6 here, and 6 divided by 3 is 2, right? Always divide first, and 2 times 2x is 4x. Yeah, I want a different pen. Here, color. This is 4x. All right, then we're going to take that 6 and go here. And this is actually a little bit tricky for some people. You need to think about this. I don't distribute the 6 to both the 1/2 and the x minus 2. When you multiply three numbers together, which is essentially what we're doing here, I can either multiply the 6 to the first number or the second. That's the commutative property. So I can either multiply and leave this 1/2 here and make this 6x minus 12. Or I can multiply the 6 to the 1/2 and leave this as x minus 2, which is what I want to do because I'm trying to get rid of the 1/2. So I'll multiply it to the number I'm trying to get rid of. 6 divided by 2 is 3. 3 times 1 is 3. So I add the 3, and I still have the times x minus 2. And that's how that works. On the other side, 6 divided by 2 is 3, and 3 times x is 3x. 6 divided by 3 is 2, and 2 times 7 is 14. And there we have it. Next, we'll distribute the minus 3, making this a minus 3x. And then a negative times a negative is a positive. So this becomes a plus 6 equals 3x plus 14. And then this becomes x plus 6 equals 3x plus 14. And we're going to subtract an x from both sides. And if you'll permit me to not write the minus x every time now, I'll subtract 14 from each side, making this a negative 8. Divide by 2, and I get x equals negative 4. All right, so if x is negative 4, we should be able to check that. Here, let me get myself some room here. Oh no, did not make it big enough. Hold on. Well, I missed the 14. All right, and I'll drag that over a little bit so I have a little bit more room over here to check. All right, here we go. Green pen and checking again. All right. 2 times a negative 4 is what we have over here. Over 3 minus 1/2 times a negative 4 minus 2 equals a negative 4 over 2 plus 7 over 3. And we are hoping that those two things are equal. So that's a negative 8/3. And this becomes negative 6 times a negative 1/2. Okay, I'm going to go ahead and get like denominators here on the right since I know I'm going to need to. I'm going to multiply the top and bottom by 3 on this side and by 2 on this side. Notice we're getting that denominator of 6. That's the least common multiple appearing again. So this becomes negative 12 over 6. Oh, you know what? That was a whole number. I could have just left that as a 1. Okay, I'm going to go back and redo that. Okay, so let's try that again. All right, I'm going to divide that and make that a negative 2. There we go. Sorry, it just would bother me if I didn't realize that 2 goes into 4. Okay, so then this becomes a negative 8/3, and then the 2 and the 6 divide to 3, and the two negatives make it a positive, so plus 3. Now I'll get a common denominator. Multiply by 3 over 3, and I get negative 6 over 3 plus 7 over 3. That's clearly 1 over 3. This 3 becomes, that's 3 over 1, so multiply by 3 over 3, you get 9/3. So this is 1/3 equals 1/3. We are good to go. Okay, and I think that was our last practice problem for that set, and it's time for some new example problems. All right, so for this problem, what I have is I got really 4 problems in one here. We're going to solve the same equation 4 different times for a different domain every time. Okay, so seriously, I'm going to solve the equation just once, but then I'll interpret my solution in these different domains. So we're going to start the way we have earlier by solving for the domain of real numbers. So this first time through, nothing's going to be any different. I'm going to add 3x to each side, getting 4x I'll subtract 5 from both sides, making that 2, giving me x is equal to 2 divided by 4, which is 1/2. Okay, so what is my solution set for the real numbers? This is my Roman numeral 1. Well, my solution set for the real numbers, I need to make sure that this is a real number. Well, it is a real number, right? 1/2 is a real number. So that's my solution set. Okay, next. This Q means rational, right? The rational numbers. The Q comes from the word quotient. So a rational number is simply a ratio, or a fraction, if you will, a ratio of two integers, which this is. This is a ratio of the integer 1 to the integer 2. So that's fine. It is in that solution set. And of course, remember also all whole numbers are considered rational as well. All integers, that is. Okay. Now, z is integers, right? This is the integers, and that is for numbers that have no fractional part. So this 1/2 is not allowed. So my solution set here is no solution. It is the empty set. So you see how my solutions change based on the domain I'm solving it over. And lastly, for the natural numbers, those are the positive integers. This is also an empty set. And this is something that you'll see a lot more of, in later math classes that you'll take in school. We'll occasionally come across it, but it's an important thing to understand that your solutions depend not just on what makes the equation true, but the domain in which you're solving. Okay, what I want you to do is to try this same kind of thing with two different practice problems. And the second one is a little weird, okay? Hopefully you're comfortable with, somewhat comfortable with your simplifying radicals. I'll just remind you that when you divide or multiply with numbers that have square roots in them, inside multiplies with inside, outside with outside. When you divide numbers in a radical with the numbers in a radical, divide the outside numbers by the outside numbers. But I wanted to show it because it's an interesting concept. So give it a shot. Pause the video. Try them both. We'll go over them both when you're done. All right. It's time to do it to it. I'm going to wrap this lesson up here. I think this is our last couple of problems. So. All right. I'm going to solve this equation over the domain of the real numbers. Right. So I'm going to add 1 to both sides. I'll go ahead and show it again. Just for funsies, 2x equals -6, and then we would divide by 2, and I get x is equal to -3. So let's talk about these solution sets. R, real numbers. Basically, every number we've encountered so far in this class has been real, so that's good. Q, rational numbers. Any number that is a fraction or could be expressed as a fraction. Z, the integers. Those are your positive whole numbers and your negative whole numbers. And in the natural numbers, those are your counting numbers, 1, 2, 3, 4, 5, 6, 7, etc. So this solution is definitely real. It is definitely a rational number because we could just call this -3/1, and that's still a rational number. And it is an integer because it has no fractional part. But it is not a natural number because the natural numbers begin at 1 and count up from there, sometimes called the counting numbers. So that one's an empty set. All right, next we have 3 times x minus 4/6 is equal to 3/6. So what I was expecting you to do, I know it's a little bit weird. I'll go back to using blue to solve, though. But what I was hoping you did was realize that, hey, this is just a number. I can add 4/6 to both sides. And when I do that, these are like adding like terms. This is no different than when you have like 4x plus 3x, right? That's kind of sloppy. Let me write that again. So I'm adding 4/6 there to cancel that out. And I am adding 4√6 on that side. So this is √3 times x, which you can just write like that. Just be careful that you I like to use the times sign sometimes or put the x in front so you realize the x is not under the square root there. Okay, 3 plus 4 is 7 root 6. So again, this is when you add the radicals, it's just like combining like terms. It's not, you don't add the numbers in the radical. Now divide both sides by root 3. And then, as I was talking about earlier, the rules for dividing and multiplying with radicals is that inside with inside, outside with outside. So I will keep the 7 divided by 1 is 7. Then I would divide 6 divided by 3 is 2. Okay, and there we have it. 7 root 2. So, first, is 7 times the square root of 2 a real number? Yes, it is. It is a real number. All right, little Roman numeral 2. What about Q, rational? Well, this is not a rational number. If you put it in a calculator, you'll see it's a decimal. Square root of 2 is a decimal that goes on forever without a pattern, just like pi. If I multiply that number times 7, it still doesn't have a pattern. This is an irrational number. So this is an empty set solution. There is no rational solution to that equation. And that is something that will be an important concept to us in a later unit. And since it's not rational, it's not an integer, it's not natural numbers, because all those numbers are rational. Okay, so that's it. The last thing I wanted you to do is to just kind of contemplate on your own. This is just closing thoughts here. The lesson exit ticket. If the value 2 is a solution of the equation 5 equals 4x minus 3, what does that mean in plain language? Make sure you have a working definition for yourself of what it means to be a solution to an equation. All right, so contemplate that, and then until next time, take care.